Well, hi. It's exactly some minutes later. I've no idea how many because I haven't been keeping track. So let's now have a look how the diffusion has gone in our cells of different sizes, shapes, and therefore surface area to volume ratio. What I'm interested in this lab is kind of the diffusion distance. So before, when we left these things for a very short time, we found that they had diffused around about, the bleach had diffused around about 1 millimeter into the structure, and therefore a very low diffusion distance was an advantage if they actually wanted bleach. Of course, most organisms don't want bleach, and so what we're doing is looking at the idea of oxygen diffusing from the membrane throughout the whole volume of the cell. Now, last time I cut the 1 centimeter cube up, and now we cut that open, and we can see that and I think it's about half an hour again since I did the last video. You can see that there's a total of about 2 millimeters of diffusion going on. So you can also see that because this is 1 centimeter squared, 10 centimeters, 10 millimeters, the diffusion distance would be half of that. The minimum diffusion distance, the maximum diffusion distance would be half of 10 millimeters. It would be 5 millimeters. It's about halfway there. And so this is going to take about 2.5 hours to reach the middle. And I'm sorry, I won't be staying at school for that long. So let's have a look at the 2 millimeter thing. So the 2 centimeter square cube. So we'd expect that to have a maximum diffusion distance of half of 2 centimeters, which would be 1 centimeter or 10 millimeters. And we cut it, and we can pretty clearly see that it's not done much. So it has gone about 2 millimeters, and you can also see that this is going to take an enormous amount of time to go fully. So let's say 1 millimeter every half an hour. And so this is going to have to be, if it's 1 millimeter every half an hour, 2 millimeters an hour, this is going to be 5 hours before it actually gets oxygen to the whole thing, by which time any cell's going to be dead. And things are, of course, worse for the 3 centimeter cube, and you know what's going to happen here. Right, like a little iced cake there, and it's gone. It's 2 millimeters, and because it's 3 centimeters, the maximum diffusion distance is half of 3 centimeters, 1.5 centimeters, or 15 millimeters, and at that 2 millimeters an hour, that's going to be 7.5 hours before it gets its oxygen to the whole thing. So it really is a bit disastrous being a large cell. This one again, a 4 centimeter cube, at that like 2 millimeters an hour, it has to go 20 millimeters, and it will be 10 hours before this one manages to get any oxygen at all to the middle of the cell. So let's have a look at these ones. So we had this idea of a 1 centimeter times 1 centimeter times 4 centimeters, and this one 2 centimeters times 2 centimeters times 4 centimeters. And I'll cut them lengthwise. So you're sure what's going to happen. They've gone about 2 millimeters. And yeah, you can see that this one, maximum diffusion distance of half a centimeter, 5 millimeters, it's going to take about the same amount of time as the 1 centimeter cube to get its oxygen throughout. So it gets more volume, so it can do more things, it can have more organelles in there, but its diffusion distance is the same as the 1 centimeter cube. So that's one way to add volume without disadvantaging yourself and not being able to get the oxygen to all of your parts. And it's a similar story with the 2 centimeter times 2 centimeter times 4 centimeter. Yeah, that's going to take the same amount of time as the 2 centimeter cube to get oxygen to all of its tissues. And so having this lengthened shape gives it the same diffusion distance, therefore about the same time to get its whole cell with oxygen diffused to it, but it manages to get more volume, which is an advantage because you can fit more organelles and do more chemical reactions. It's a really simple demonstration, I know, and you're probably going, but it's quite a good demonstration of the importance of surface area to volume ratio, and more than that, maximum diffusion distance.